At some point in your programming journey, you may have encountered a situation where simple arithmetic operation doesn't really yield the expected result. At that point, you might just have shrugged off it as a generic rounding error. Then you might have seen this infamous joke about JavaScript not being able to handle simple math. But then you quickly realize that it's not only JavaScript. For some reason, adding 0.1 plus 0.2 doesn't add up to 0.3, where the rounding is needed. What's going on? Well, let's break it down. The core problem lies how we and machines interpret numbers. Humans naturally think in base 10, well, because we have 10 fingers. And we can break any number down into the combinations of powers of 10, that's we call it base 10. For example, 453 we can express simply as 4 hundreds, 5 tens and 3 ones. But computers do things a bit differently, because they consist only of transistors, which are basically switches on and off, ones and zeros. So everything has to be transformed into this binary representation of ones and zeros. And it's quite easy. The same way as we construct numbers using powers of 10, we can construct numbers using powers of 2. For example, number 453 can be converted into the base 2 using just 9 bits. We can quickly spot that to create this number, it is a combination of 256, 128, 64, 4 and 1. So combining those together yields the result. So let's switch those bits as on and we get our binary representation. Of course, there is a more general way how we can transform that number using a remainder method. Let's repeatedly divide the number by 2, taking notes of the remainders, until we get down to 0. So starting by this 453, we get 226 and with remainder 1. We note it down. Then 226 divided by 2 gets us to 113 with remainder 0. We note it down also. 113 divided by 2 is 56 remainder 1. Then it's 28 remainder 0, 14 remainder 0, 7 remainder 0, 3 remainder 1, 1 remainder 1 and 0 remainder 1. And that's how we get our binary representation in this general way. So whole numbers are quite easy, but what about decimals? That's where the things get messy. Similar to decimals, binary also can have fractions, where after this dot, each bit represents a negative power of 2. So summing all of these power of 2 results in 6.625. Now to have a generic conversion of any decimal into binary, we actually do that in 2 steps. So if there is an integer part, we handle it with the remainder method as discussed previously. But for the fractional part, we multiply everything by 2 while taking notes of the integer part until we get 1. 0.625 times 2 is 1.25, that is 1 integer, so we mark it as 1. 0.25 times 2 is 0.5, 0. 0.5 times 2 is 1, 1 we stop. Seems simple enough, but here is the catch. Like in the base 10, we have numbers like 1/3, which cannot really be written down exactly in decimal format because they turn into an infinitely repeating pattern of 0.33333. Same goes from binary. Some fractions turn into infinitely repeating patterns of bits. For example, this simple 0.1, if transformed into binary, ends up in 0.2, then 0.4, 0.8, 1.6, 1.2, 0.4, wait, we already saw 0.4. It's a repeating pattern. It means that 0.1 is represented by this infinite pattern of bits. Well, in theory it's fine. In practice, our computers have limited memory, so we'll have to cut it off at some point. Because of that, computers only really store an approximated value of 0.1. So it means if you perform any operations with this number, it ends up with only approximated result. And that is the reason why 0.1 plus 0.2 does not match to 0.3. But when and where this cut off is actually happening? Well, it's straightforward to convert between the systems. It's not really practical for computers to do in such a way that we just discussed. To make things more practical, compute follow floating point standard. In this case, it's 754. Numbers stored in memory are actually made of 3 components, which is sign, exponent and mantissa. You can think it's like a scientific notation, but in binary. To transform binary into this standard, we need to perform following steps. First, we normalize the number by moving the dot until we get 1 point something times power of 2 and how many times we moved the floating point. Now we need to extract the exponent, which in this case is -4. But because of the precision, we need to add it to the bias. In the 32-bit case, it's 127. Then the sign can be easily extracted as either 1 or 0. And last is the mantissa. Depending on the precision, it is controlling how many numbers after the dot we actually are storing. And this is where the rounding occurs, because in for example, in the single precision, it only stores 23 bits. yielding us a floating point number representation in the following form. So when we put everything back into the formula, you can see that it doesn't exactly match the point 1. Okay, I think it's enough with the theory alone. Let's do some practice and see it in action, how the values are represented and handled in Java, for example. So let's take our integer value that we had, 453, and we would like to transform into the binary and see how it looks like. We could write our remainder method and do it manually, but in Java actually there is functions already built in that can do that for us. So for example, this integer can be converted into the binary using an integer to binary string function, providing this integer value. And let's output that in console, and we can see our binary representation. Let's quickly verify if that value matches. So it's 1, 1, 1, 0, 0, 0, 1, 0, 1. So each of these positions are just powers of 2. So the first position here is 2 to the power of 0. This one is 2 to the power of 1, which in practice is actually 1, 2, next is 4, 8, 16, 32, 64, 128 and 256. And our goal is to sum up those values which have bit set to 1. And that should give us the decimal result. So in our case it's 256 plus 128 plus 64 plus 4 plus 1, which indeed does match for 153. So you can see that it has been converted successfully. But for decimal and fractional parts it's not quite straightforward because we do not store them in this plain binary, but rather than following the standard. So for example, if I would have my value 6.625, I can get the bits how it is being encoded in memory using the function float to int bits and provide our value, and let's output those bits. But we can see we end up with some strange value, which is not really a binary representation. Well, technically it is, but Java is trying to convert it to an integer. Instead of decoding it to integer, let's print it as it is. And this is our float representation. So the first bit is the sign, next 8 bits are the exponent, and the last 23 bits is mantissa. And that's why when printing to number we see some strange integer, because this binary string is trying to be represented as integer. And that is not the correct way how to do it. The correct way would be to extract our all three components. And if we open this function's documentation, it says that we can actually do that by using bit masks. So if we take 31st bit, we will get the sign. If we get bits from 30 to 23, we will get the exponent. 22 to 0, we will get our mantissa, or the significant, how it's called. So for the sign, we want to shift for the 31 position and apply our mask. Same goes for the exponent. Let's take our bits and shift for 33 and apply our next mask. And things that has been left will be our mantissa if we apply the mask. So let's print and see what's inside. So sign is this one, then the exponent, and our mantissa. So you can see the sign is 0 because it was positive. So if we would have a negative number, we would get sign as 1. The exponent is 129. We didn't move that dot so many places. So well, actually remember there is a bias inside. We need to remove it. So after the transformations, let's remove the bias for the single precision. So our exponent is 2. Now for mantissa, you can see again, it's quite strange number. It is not really representing basically anything. Well, because it's again trying to interpret the bits as integer. To get number, we need to convert it back to the floating point number, not the integer representation. That we can quickly do with transforming back into the float representation. So at the first glance, yes, indeed, it does seem quite complicated because those are binary operations, but this is not the point, because you could just do the same thing with the strings. The main point is that we can get all of those three elements from our binary representation. Now that we have it properly extracted, we can see that our sign is 0, exponent is 2, mantissa is 6, 5, 6 to 5. Now we can reconstruct the number back, and we can do that by following this formula. So minus 1 in the power of of the sign. So if it's a negative, it will be 1 and it will keep this -1. If it will be 0, it will transform to 1. Then 1 plus our mantissa value times 2 to the power of our exponent value. So value is taken, let's have it like value 2, and let's then output it value 2. And you can see that it matches the original value that we encoded. So 6.625, and here we also have 6.625. Everything is great. But now what will happen when we'll take our point 1 and we get a finite representation of this string? You remember that it repeats itself. So you can see 1100, 1100, 11, it's infinite string of bits. But because we have some sort of precision, we have limited number of the mantissa bits. In this case, okay, sign again is 0, the exponent is -4, the mantissa after it being truncated resulted in 0.6, which if put back into this formula, we get actually not the 0.1, but 0.1000149011612. So it differs, it is not exactly 0.1. And same goes for 0.2. If we do the math on 0.2, you can see that it is not precisely being stored in memory. And that's why when we add 0.1 plus 0.2, we end up with this error. Because when you are doing math operations on not exact values, of course, you will not get exact result. So while it's not a problem, it's a fundamental thing how binary system works, we need to somehow fight this problem, because otherwise, we will have always faulty results. And you can imagine in financial use cases, this is not acceptable result. Well, for that, there are multiple ways how to go around this issue. One approach is do nothing, because many problems do not require you such precision. Like if you're calculating offsets or positions of characters in games, if you will have some sort of point, I don't know, 9 elements after the dot error, it will not really affect how the person is rotated or how it locates. If you need precise, for example, if you're working with some sort of currencies, one way how you can solve this problem is to work with integers instead. Think of, instead of trying to represent monetary values within dollars, like I have a half a dollar, try to represent it in cents. So if I would have 0.1 as 10 cents, instead of 0.1 I would put 10, and for the 0.2 I would put 20. Of course, the obvious is that when I will count them together, there will be no error introduced. You can see that it's 30 cents. And performing such operations with integer are much safer because we are not introducing this floating point arithmetic. And then we are trying to limit the use cases when we are going back to the floating number. For example, if you want to show it on UI, then let's just divide at this point the result by 100 to show that it is 0.3. Another way is if you're doing some calculations and you are fine with some little error, do not compare them with equality. So if I would say if 0.1 plus 0.2 is equal to 0.3, you can imagine that in the result I will get false because it is not. But if I talk about similarity, so I could calculate the distance from this result to the expected one. So if I run it, you can see the difference between these values are so tiny. It's 17 places after the dot. Then if I have some sort of tolerance value, for example, how it's usually called epsilon, and I say I'm fine if the error will be within 9 decimal places, then I can say if this distance between my results is less than my agreed epsilon, then I will consider them equal. And last but not least, if you need to work with really exact values, then we have different arbitrary precision libraries. Like different languages have different libraries. In Java, probably you have heard about the big decimal. So you can say and make here big decimal. So using big decimal, you are not representing the values following this standard. So this allows you to have different kind of precisions available. And you can see if I will put these two values and output their sum, I will get the 0.3 exactly. Because they're arbitrary precision libraries, they will handle this problem, they will work around it and have your exact measurements. Of course, it will either take more memory or will take more computations, but if you need these precise calculations, you have to do that. But you need to be very cautious with them, because you can see that I have put them in the quotes. Why have I done that? Because if I will remove them, actually this will be handled by Java before the big decimal even touches it. So here it will introduce this rounding error. So if I will run it, we can see again this error number that is not matching the 0.3. Why? Because again, Java has interpreted it, it has stored it, it has handled it. But if I take it as a strings, then I do the parse, then I leave the parsing to the big decimal, and it will transform it correctly. So be aware. So this was our little deep dive into floating point arithmetic, and you saw how this quite simple arithmetic expression can lead to rounding errors because of the binary representation of the numbers in the system. We talked about how this error occurs. We also have talked about how we can mitigate this issue. But realistically, in most cases, you probably will not do anything about it, but you need to be aware. When you're talking about some precise measurements, some precise operations, this can lead to a quite large error. So we need to get used. We are always working with some sort of approximations, right? Because there are also like these rational numbers like pi. We cannot represent all the digits fully. We cannot even write down them on paper. So you can see that it's not really a bug, but it's a fundamental property of how computers store numbers. So next time you hear that your programming language X is bad at computing, tell them to check their own favorite language.